Yes, thank you, Katie, Ramesh, for your presentation, your nice presentation. And you have a different question. You can ask again some question in the chat, and now with Eric and me, we can publish the question in the chat. There are different questions about the amazing experiment with human sample. Because it is very special. In fact, Rémi Villinger asked to you the order of magnitude of brain strain during your test, and I have a similar question about the strain rate or the acceleration imposed during the test by the mechanism, and if it is possible also to measure the acceleration in the head or the strain value or something like that. So there are different questions about that, about your experiment.
Right. So the strains, so these live human experiments that we do, they are very highly controlled, of course, because we cannot injure the individual. And this is really important to us. So we have to go through a bunch of protocols and get approvals to do these kinds of experiments. So the strain is limited. The strain that we get is around 3%, and sometimes, so we aim for around 3% strain. Sometimes, in some cases, we end up seeing 5% in some individual parts of the brain, but we're aiming for 3 to 5%. These strain rates, therefore, are very low. So if you think about it, you're talking about strain of, let's take the highest strain, 5% over 30 milliseconds, right? So it's 5 times 10 to the minus 2 over 30 milliseconds. That gives you the strain rate. So it's relatively low. You do not need a high strain rate, though, to cause injury. Behavior is strain rate dependent, but most injury that is observed is at relatively low strain rates. The accelerations we are applying are usually in the range of 100 radians per second. We're not very much higher than that, again, because we want to limit the potential for injury. So yes, we can measure that. We do measure that. But we deliberately ensure that none of these can reach anywhere close to the threshold. To give you a sense of things, the injury threshold is likely around 18 to 20% strain. So if you're staying at below 5%, you're safe.
Okay, and we have another question about your experiment. To Fabrice Piron is here with us, and he asked for the images obtained with different slices. Are there repeating the in movement as many times as you need the 2D target slice? So you need the loading to be repeatable. How is it possible? Because in fact it is with human sample and the movement is not similar, and perhaps the movement of the head can be different between different tests.
Right. So it's a very good question. Hi, Fabrice. Yeah, this problem is a fundamental problem for us. So the way the experiment actually works, you do not get all of those slices in one shot. You're not getting all of them in one test. So realistically, what happens is the volunteer gets in, sits in the MRI, actually starts by sitting outside the MRI, and practices making this motion. And they do that a few times until they feel comfortable with it. Then they go inside the MRI, and then they might do 35 or 40 motions. And during each of those motions, we're taking a different slice. Now, most of the time, early on, they will not be repeatable. The volunteer is not able to do things repeatedly. But after some time, volunteers learn the process. They become very comfortable, they relax, and then you get repeatability. With some volunteers, we never get repeatability. And so we just have to throw that data away. But with others, we usually get that. So right now we have something like 55 volunteers who've gone through the whole process for which we have good data.
Okay, and I check if we have another question about your experiment. There is a question about your experiment on Mickey Mouse at the end of your presentation. Perhaps it is really surprising. Caroline Beck said, did you plan to do same experiments on rat mouse with injuries? Did you try to do that?
Yes, we have done those. We have done those on rats as well as mice. We decided to focus on mice. It's much easier to do the mouse experiment. So we have done a few of them on rats. But yes, we've done interview experiments on mice, so that data is available and we're working our way through it. Some of it has actually been published by Vasily Kolyotsos in a couple of papers that I can send to whoever's interested.
Okay. And about the model, we have a different question. It is very interesting because first, Pierre Pradel asked a very specific question. What are the advantages of using MPM instead of FEM? This is a competition between the different modeling with discrete element modeling, MPM and FEM. Could you precise the advantages for you?
Sure. So I use both. So for the mouse, for instance, I'm using primarily FEM. But for the human, I'm using primarily MPM. There are two reasons. One, and this is really important, is for MPM, one of the big strengths is I can go from voxelated information. So my imaging, right? My imaging is three-dimensional imaging, so I get voxels from the images. In MPM, I can take a voxel and I can make it a cell with a material point inside it or multiple material points inside it. So there is no meshing question. I immediately develop the structure of the brain. Directly from the experimental image, I get the structure. So that is very valuable to me because I'm doing subject-specific experiments. So that's one. The second is scalability. So I can run an NPM simulation with very large numbers of particles, 1 million particles, very efficiently, because that particular framework, the NPM framework in Uinta, is very highly scalable in terms of parallel processing, because it was really built by a lab that's interested in, they're computer scientists, they're interested in being able to scale. So this thing can be run on a big DOE machine with 100,000 processors and still scale. Whereas when I do FEM, I cannot scale beyond 25, 30, 40 processors effectively. It's not efficient. So when I need the high resolution, the NPM becomes really valuable.
Okay, and to continue about your modeling, in fact, usually when we have to speak about simulation and modeling, and if we have the uncertainty about the modeling, it is really interesting to speak about boundary. And classically, we have this kind of question. First, there is a question about the personalized head model, how it is possible to adjust the model of a specific head to be close to the shape of the head of the human sample, for example, or if we change the shape of the head, is there any variation of the results? It can be interesting to know that. And a second question is concerning the boundary. It is exactly did you model other organ? Is it possible to model the organ close to the head? François Janka asked, how the other organs are modeled for the human finite element model? Do you know the uncertainties due to this hypothesis?
Right. So there are sort of three different questions. So let me start with the first one about the subject-specific models. So remember, the way I'm doing this is I start with imaging. That's what defines a subject for me. So I've got the MRI images of that individual's head. And I go from the images directly through MPM to the model. So I'm not taking a model and making it fit the subject. I build the model for the subject because each voxel in the image for that subject becomes part of the MPM calculation, which is one of the strengths of the MPM in the first place. So in that sense, I don't have to fit each of the pieces. So this is one of the problems I had when I was trying to use FEM to do this, is to go subject specific was just incredibly expensive, because effectively it was like building a new mesh for every individual. And that just became very expensive. The second question with respect to uh, the boundaries. So this is an important one. So boundaries in MPM are not as clearly defined as when you think about boundaries in FEM, right? So in classical finite elements, the way you define your boundary is something you know very well. But in MPM now, you're going to have basically the voxel resolution is what defines your boundary. And so it's always hard to define the boundary conditions the same way. That's a mathematical problem, but there's a different biological question that's really important. So the brain and the skull are separated by this membrane, a set of membranes called the dura and the pia. And then there are these bridging veins that sort of go across from the skull into the brain. So that's a kind of boundary condition between the brain and the skull. We do not model that well at all right now because that is not when we do our imaging. So we don't have a good sense of what that is. So that's one of the weaknesses of our model, is the boundary between the brain and the skull is not properly captured. We essentially create an artificial thickness there and we fill it with something like a fluid and say that's it. So that is not well done. And in fact, as we did work with the vasculature, with the blood vessels, it turns out that is really important. So that's an area where I think if we can get more investment of effort in the community, that would be very good. Understanding the material properties of that layer. There have been some experiments that have been done in that, particularly at Utah, but there's just not enough data. Let's see, the third question was about uncertainty. And this is, of course, a classical question and a really important one. So there's uncertainty that propagates through this entire system. There's obviously uncertainty from the imaging end. So what kind of structure do you have? Basically, even what anatomy are you putting into your model? There's some uncertainty from the resolution of the imaging. But then there's uncertainty associated with the material properties and how that goes in. And then there's uncertainty associated with your boundary conditions and how those go in. So you've got to track all of those. So right now I have a postdoc working on that. We're using a framework called UQPy, built by a colleague of mine, Mike Shields. So basically this is a framework that allows you to take a given model and look at the uncertainty propagation inside that model. You build a surrogate model, you run lots of calculations from the surrogate model, and you can see how the uncertainty propagates through. If whoever was interested in that, be happy to communicate with them offline, and I can show them how we do it.
Okay, and concerning your simulation too, in fact, Fabrice Piron asked if you could potentially identify the material properties in vivo from the target MRI data by equating inertial virtual work with strain virtual work. Did you attend this?
So yes, we have, and it's difficult because you can't get the volunteers to go through very large numbers of motions, right? So there are only 2 or 3 motions we're trying to get them to do. So right now we only do this motion and that motion. And so it's a small number of states for which you have the tissue data. So you can extract some properties. An easier thing to do is to think of this. There's a technique called magnetic resonance elastography, which looks at wave propagation in the brain. And you can use that to get the linear viscoelastic properties of the tissue in different parts. So think of that as a baseline. And on top of that, you superimpose these large motions, and then you can try to calibrate a consider function from those large motions. So we try to do it that way. The big difficulty is always accuracy. So the imaging in the experiments is 1.5 millimeter kind of cubes. That's what you're thinking about. The highest resolution we can get is maybe just under a millimeter. But when you go to the high resolution, it's harder to get the same time resolution. That's this typical trade-off we have. And the time resolution we have is actually, this is a complicated one. The way they analyze those images, it's not the time series way in which we are used to doing things. They are essentially, it's like having for each particle, you have like a kernel around it. Information from that kernel gets propagated into where the particle is. And so the real world resolution of the imaging is not as good as we need to actually extract material properties uniquely. You need some initial estimate, some idea of where you're going, some kind of model, and you can calibrate. But I don't know that you can extract from scratch. Just don't have enough.
And in fact, during your experiment to evaluate the property of the brain, in fact, it depends obviously of the velocity of your test, of the strain rate, and we have a question concerning the duration of the impact during the simulation. Model validation happened under 40 millisecond duration, whereas impact it is just a 10 millisecond. So if we consider that the property and the behavior of the brain can be viscoelastic, it is difficult to evaluate the properties of this behavior in changing the strain rate imposed or simulated. Could you comment that?
Yeah, no, this is a good point. And the brain is viscoelastic. Oh, no question about it. It's not linear viscoelastic, though. It is non-linear viscoelastic. And this is our big problem, is basically for different strains, right, you have different effective damping, if you like. And so we don't have good enough data to be able to track all of that. So we always, it's like doing piecewise fitting. You have this much data, and then you extend it a little bit, and then you extend it a little bit. That's how we're going at it. The question of time scale is an important one, though. So I want to talk about this from 2 points. One is, in our experiments, the typical time scale is maybe 40, 45 milliseconds. We are imaging over maybe 100 milliseconds. Actually, we image to 150 or so milliseconds, but after 100 milliseconds, the quality of the data drops. So the data is not as good, just because it's hard to get repeatability. That's one. But the other thing to remember is there is a difference between the impact problem and what happens in the brain. So you might be impacted, somebody hits you on the head, and that's maybe that's an impulse that has a 2 millisecond, 5 millisecond duration. But the deformation of the brain takes much longer than that because of the wave speeds. And in fact, you're looking at the interaction between the time scales for wave propagation of the brain, not just viscoelasticity, and the time scale of the load. So even if your last wave went by in a few milliseconds, the center of the head doesn't know about the rotation for 30 milliseconds after that. And so that propagates through the system. The other big effect that shows up in live humans is the neck. Someone who has a stiff neck, the way in which their motion occurs is different from someone who has a soft neck. So essentially there is a constraint, a boundary constraint that you provide with your neck. It's one reason why athletes don't get hurt as easily. They have very strong necks. Most of us don't.
Yeah, and we have also different question about the variation of the properties depending of the different brains that we can have. If we consider a different part of human, such as bone, we know that there is a variation between different samples, and it depends also on the age of the bone, on the age of the people. Is there any information about the variation of the brain properties mechanically with the age? And we have also we can have also a question between a baby and an adult and old man, for example. And we have a question between also human and mouse, for example, because there is there are two presentations of your experiment.
Yeah. So this is an important one. Yes, there is a difference in tissue properties with age. How big the difference is a question of debate, because there are not that many measurements. There are quite a few measurements in animals, so in pigs, for instance, for baby pigs and moving up, and you can see there is some evolution with age. So one of the big difficulties in the overall material property space for brain tissue is the properties, yes, they change with age, they may even change, well, they clearly change with location in the brain, but they change much faster with things like chemistry and humidity and how long it's been after you took the brain out. So if you excise the brain, a piece of tissue from the brain immediately after death and measure the properties versus measuring the properties 6 hours later, it's completely different. And so the difficulty is that when you look at the literature, right, someone did it, immediately, someone did it 24 hours later, someone froze it and then thawed it and did it again. So we think there are variations in these properties with age, but it is not clear how much of that is experimental artifact and how much of it is actually there in the live human. We are hoping to get some of that from the MRE data. At least you can get that for different ages and we can compare that.
Okay. And in fact, because Natasha Elster asked which metrics are impacted by the scale law, you use between a small size and the big size between humans and mouse, for example, because there is a strong difference of scale, obviously.
Yeah. I don't know the answer to that. I think this is an area for us to do some work. I'm hoping to build an analytical way of thinking about this, but there's sort of the scaling associated with the way I tend to think of this is that there's the physical size, and then there's your boundary condition that's applied. But at the tissue level, I think that's where you can tie these scales together. So what does that mean in terms of scaling with respect to size? I think that's much harder to do because it's also scaling with respect to geometry. You mix the two things. You're not just scaling size, you're changing shape. So I don't have a good answer. I think it's a great area for me. So okay. I think analysis would be useful there more than experiment.
Okay, I checked the question in the chat. I have a remark of Bradley. He said that he had a TBI in 1947. He asked to you if you are agree that it would be useful to donate your brain to the brain center where you live. I'm not sure that it is a question, but perhaps I don't know, Bradley, if it is a good idea. Perhaps, Cathy, you can answer to Bradley directly.
I think we can do that offline.